Good afternoon, everyone. A warm welcome. Myself, Gaurav Nandi, research scholar from Center for Nanotechnology, IIT Guwahati. It gives me immense pleasure to extend online familiarization workshop on 2D semiconductor nano devices and simulation on behalf of INUP I2I team. First topic of day 2 afternoon is on material simulation tutorial, graphene and other 1D or 2D material simulation and post processing by Mr. Deepak Upadhyay. Mr. Deepak Upadhyay is an application engineer at Impulse Technology. He completed BTech with electronics and communication engineering from Dr. APJ Abdul Kalam Technical University, Lucknow, Uttar Pradesh. Previously, he worked at Leeway Design Consultants India Private Limited, Gurugram, Haryana as a junior design engineer. Recently, he is working on EDA tool called Nano Academic. He will show his presentation and demonstration on 2D material simulation tools, NanoDCAL software from Nano Academics Technologies using DFT and its application in current and future technologies. With this brief introduction, I would kindly request Mr. Deepak Upadhyay to throw light on the topic. The participants are requested to keep their mic muted and drop their queries in the chat box, which will be taken by the speakers and at the end of this talk. Over to you, sir.
So good evening to all of you. Myself Deepak Upadhyay. So today we have a webinar on nanomaterial and nano device simulation using NanoDCAL and RESCU software. So first of all, I would like to show you some presentation, and after this presentation, I would switch on the demonstration part. So this Impulse technology is based in Gurgaon, which provide nanoscale device and material simulation software, optoelectronic device simulation software, and cloud-based material simulation software. And my most valuable partner, that is Nano Academy Technology. This Impulse technology is a distributor for this Nano Academy Technology software, that is a Canadian-based company who provide a nanoscale simulation tool where you can simulate crystal, molecule, device, carbon nanotube, graphene, etc. And if you want to work in optoelectronics domain like perovskite, tandem, organic solar cell, thin film, OLED simulation, then we have another partner, that is Flexim, that work on optoelectronics domain. And if you have any problem in your cluster, suppose you have some SPG server that is not good for DFT, then we also provide the cloud-based software so that you can run the calculation online on Amazon server, Google server, and you can download your result from online cloud resources. So these are three major partners that we are presenting in India. So today we have the webinar on this Nano Academy technology and its product. So we will focus about this Nano Academy technology. So this company was founded in 2008 by Professor Hongo, Dr. Zhu, and Dr. Lee from McGill University. It was developed for molecular quantum transport calculation around more than 10 plus years, and they enhanced their feature for material development through advanced digitalization and modeling tools. Now they are also emerging the field that is quantum technology, and this quantum transport simulation software is also developed by this Nano Academy technology. We have several unique features and more development are released day by day. They are basically located in Montreal, Quebec, Canada from McGill University. So this is a brief company overview. If we talk about this software, how was NanoDCAL developed, from where which the general was started. Basically in 2001 from McGill University, where Professor Taylor, Professor Hongu, who developed the quantum transport package first, and which is also supported by some Northwestern University in 2002. And in 2008, we have laid this foundation of Nano Academy technology, and officially this Nano Academy technology was released commercially in 2009. So this NanoDCAL is basically a background calculation engine that run the DFT calculation, NEGF calculation, Boltzmann constant. So all the background calculation can be used by this NanoDCAL software. Apart from this calculation engine, the user interface is there so that you can model the structure very quickly. So user interface will help you to model a complicated or simpler structure, and you can do some modification manipulation in atomic structure or device structure using interface instead of writing the script. So you can concentrate on your research, and this software is very user friendly. Even recently NanoDCAL Plus version is launched. So if you want to work on advanced level large number of atom and device structure, so NanoDCAL Plus version will be helpful. This is a general overview of our tools. So basically both RESCU and NanoDCAL, which are two main brand of material simulation tool. They include a broad range of advanced material for simulating complex material property at different level. Also, they have a tool and toolboxes that can be used for effectively preparing the calculation, executing the calculation, and analyzing the result that come out from the atomistic simulation. Now this NanoDCAL is very state-of-art general purpose first winful quantum transport package, which is both combine both DFT and NEGF function. And this software is written in MATLAB language as well as in C language. And this software is used in lot of publication papers and good journal. You can find on the Google Scholar page, which is very popular outside the India, and where many of the paper published in many domain like spin tonics, battery and energy device, insulator, photocurrent, molecular electronics domain, and it cover all the application. It can focus on electronics property as well as quantum transport, spin tonics, IV calculation, field effect, dielectric effect, spin tonics, collinear, non-linear, spin orbit coupling, all common analysis like density of state, phonon density of state, local density of state, band structure, complex band structure, thermal transport, phonon tool calculation. So this all feature will be there, so you can model the structure very easily. And you can also define the electrode for 2 terminal devices, 4 terminal devices, 6 terminal, so up to 6 pro devices structure you can simulate. You can define left electrode, right electrode, front electrode, bottom electrode. So this type of structure you can also study from this NanoDCAL software. From this RESCU software, you can study like LDA, ZGA, meta-ZGA, hybrid function, collinear spin, non-linear spin, spin orbit coupling. And here in terms of accuracy, RESCU also cover all the steps in the accuracy level of the atomistic simulation. So one of the main advantage of this RESCU is that it cover all the accuracy level of electrons in the material. In terms of analysis tool, we have a very complete list of analysis tool. For example, here you can see this is the result of band structure calculation and density of state calculation with RESCU. One of the main advantage is that they cover a few main basis set that are used in material atomistic calculation. Here, for example, you can see the result band structure for numeric atomic orbital and real space basic set calculation. And this is very important part of RESCU, which gives the user the ability to benchmark their simulation. And one of the main advantage of RESCU that it has gathered all the different approach of atomistic simulation under the umbrella of one software. We have a very powerful DFPT toolbox. Also, this is one of the main strength of this RESCU. So basically, by using this DFPT toolbox, we are able to calculate a variety of material property that are based on response of material to external perturbation theory, such as dielectric constant, vibrational property, phonon, optical property, interaction of electrode with photons, which is a representative of this temperature in the material. So with the DFPT toolbox, we are able to cover and simulate many properties. So currently with DFPT toolbox, cover response like electric and atomistic, atomic displacement, perturbation. And this is important feature, important material property, and important spectroscopy tools such as Raman spectroscopy. They are actually based on this kind of material response to XML probes, and we are able to cover that simulation, perform those kind of simulation. And one of the main advantage of our DFPT is that the state of art solver by BICG conjugate gradient method, and also state of art solver based on the Chebyshev filtering method. So basically we design these two solvers. Now, the bigger application of this software are for molecular structure simulation, molecular material-based device simulation, surface simulation, 2D material-based device structure simulation, complex material simulation, hexagonal material, some tetragonal and tri-black phosphorus material, interface between different geometry and different symmetry, and some carbon-based material, different alloy, different doping, structural defect, and other type of defect can be simulated. Now, this advanced tool are there for building this structure. You can build your crystal structure, molecular structure, device structure, and manipulate this property. You can manipulate the various lattice parameter, alpha, beta, gamma value, ABC value, primitive cells, conventional cells, even armchair, zigzag type of graphene, nano ribbons, grain boundary, different tool are there that will help you to build your structure. So advanced tool are for the building the structure along with the user-friendly interface, so that you can set up the parameter like DFT parameters, electron temperature, cutoff energy, K-point sampling, iteration control, spin type calculation. So all steps you can define. Also, you can calculate the various property like electronics, structural, optical property, thermal property, magnetic property, electronics property, and thermal transport, electron phonon coupling property. So this type of structure you can calculate by using this NanoDCAL software. These are for the material. Apart from that, certain device property are like this IV calculation, photocurrent, conductance, thermoelectric effect. So that I will show you during the live demonstration. Now, this nanodical can also work on spin-tonic domains apart from the semiconductor, material science, graphene, and other 1D and 2D material. It can work on the spin-tonics application for next generation nanoelectronics and device configuration for low power consumption that will increase your performance. And it cover on the spin moment, spin up, spin down calculation, nano ribbons, and different other kind of structure can be simulated. So if you want to rotate or define some photons, some minimum and maximum energy, polarization, theta, phi, so this type of structure you can simulate. This nanodical can also work on photogalvanic spin tonics device. You can design a multi-layer structure, monolayer structure, bilayer, tri-layer, or multiple layer structure. Like there are 3-layer structure. This graphene is sandwiched between 2 boron nitride, where you can see left region, right region, and center region is defined. Middle one is also called the scattering transport region. So you can define the left electrode, right electrode, front electrode, bottom electrode, top electrode. So apart from the left and right, you can also define the cathode, anode, and you can also define gate terminal. You can also define magnetic moment at different edge atom. And this is the stagger potential that is produced by 2 boron nitride, and different spin calculation, spin up, spin down calculation. How much will be the band gap? You can also calculate. Apart from this, nanodical can also work on semiconductor device application, molecular electronics calculation, molecular material-based device structure simulation. So you can see in the picture, this is the device where we apply some gate voltage, and you can find the IDVD characteristics, IGVG characteristic, transmission spectrum, photocurrent, and other calculation. And if you want to work on twisted graphene layer, like here you have a planar sheet, and that planar sheet you want to twist on particular angle or particular radius. So you can also study the electron transport by twisting the graphene layer. Suppose you have a sheet of graphene, circular region, left and right region. You want to rotate upside at any angle. we have angle position, and where you can define what position left and right electrode you want to rotate in which direction, and accordingly you can find the EK diagram, transmission coefficient, eigenstate, potential, distribution, and many more property by rotating or twisting the sheet. And if you want to work on 4-terminal devices, 2-terminal devices, nano ribbons, nano wire, grain boundary, surface structure, crystal structure, molecular material based structure, like this is the device where left side, right side, and bottom and top side electrode are defined. And you can study the IDVD characteristics, band structure, conductance, and other property can be calculated. Similarly, you can rotate your tube at any angle, and based on the rotation, how much will be the defect in your sheet, you can also study. Just a few words about the feature and the characteristics of our tool. So that our tool include many features, pretty unique features, atomistic and quantum transport features. Also, we can predict the material property, in general, all the material and electronics property. That is very useful. And we offer a fast converging tools with advanced algorithm, and we also offer a powerful feature including machine learning tool, and we offer efficient parallelism and a scalable design in our course. So plenty of tutorial are there, and we offer an extensive documentation and tutorial for our user to get started and get proficient quickly. And to enhance the user experience, we offer a user-friendly graphical user interface such as Python API in the new version. And we also enable the integration of third-party solution for plotting or displaying the curve. For the rest, yes, notably, we offer a free 1 year service for advanced technical support of our tools. And we provide a free trial license as well for our product, typically for 1 month. And this is the rescue another module inside this NanoDCAL that can work on the large number of atomistic scale calculation, DFT and DFPT, optical and battery property. So now I would like to demonstrate you live in this software that how you can import the material, design the material, manipulate the structure, define various parameter, DFT parameters, apply some voltage biasing, and analysis of result that can be demonstrated now. So thank you for listening this presentation. I would like to start the demonstration part. So this is my device studio, that is a user interface for this NanoDCAL and RESCU software. I would like to open this device studio, go to the Win folder, and here the device studio is there. I would like to click on skip login, and from here, if you want to create a new project or want to work on your existing project, so you can click on it. Either you can click on create a new project. So I would like to start from the scratch, click on the create a new project and click on the OK. Here you can define the name of your project. And you can click on the save option. So this is my device studio, that is a user interface for this NanoDCAL and RESCU software that will help you to do some modification, manipulation in your atomic structure and device structure. First of all, I would like to click on the file. Here you can see in the file, if you want to open your, if you want to create a new project, or if you want to open your existing project, you can save your project. You can design a device structure, crystal structure, molecular structure, and you can import your material. So this software support two type of importing the material. Either you can import from the local database, either you can import from the online database. So suppose I would like to click on the import local, and here you can see this is the material database of this software. Here you can see like 0D material, 1D material, 2D material, 3D material, and some organic material is there. In 0D material, some molecule, amorphous and crystalline is there. This is the amorphous, and this is the crystalline. Here, this is the 1D material. In 1D, this is the nanotube, different combination of Kroll vector. And this is the 2D material where you can see novelty material, some arsenic, bismuth, black phosphorus, and this is the graphene. This is the 3D material where you can see conductor, insulator, layer material, magnetic material, metal oxide, novelty material, semiconductor is there. In conductor, you can see this is the pure metals. This is the database of pure metals. And this is the insulator. And this is the layer material. And this is the magnetic material. This is the metal oxide. Novelty material, some perovskite, topological insulator. This is the perovskite. This is the topological. And here you can see this is the semiconductor. So the conclusion is all about that. This is the material database of this software. So if you want to create a crystal structure, so you can click on the file option, go to the new, and here you can see this is the crystal builder. We have a lattice space group information where you can see 1p1, 1p2, 1p3, and accordingly you can select monoclinic, simple clinic, FCC, BCC, and Brevius lattice. Whenever you select this space group, the Brevius lattice will automatically selected. Suppose if you want to create a black phosphorus with structure, crystal structure, so simply you can select the space group, and according to the space group, the Brevius lattice will automatically selected. So this is the orthorhombic base centered cubic structure. Here you can also define the ABC value. This is the 10.478, and this is the value of C. So as per your requirement, you can study like ABC value, whatever value you want to, and you can click on the plus icon. So the default carbon atom is selected. So if you want to remove from another atom, so double click on the carbon and the periodic table will open. So from the periodic table option, you can select any atoms. So I would like to click on phosphorus and click on OK. Here you can also change the coordinate point of this phosphorus. So any value you can change. This is the P2. And this is the P3. And here you can see like primitive cells, conventional cells. So this type of structure you can show, like this is the primitive cells and this is the conventional cell. You can click on the preview. Here you can see this is the primitive cell, conventional cells, and click on the build option. So the black phosphorus based crystal structure has been created in my database. And if you want to design a molecular structure, so click on the build option, go to the molecule. And through this, you can do some 3D molecular modeling. And this device studio added support for the 3D molecular structure, import and export function. And a 3D molecular modeling function include element fragmentation tool for each element, through which you can easily and quickly build 3D structure.
Sir,
And suppose,
excuse me, sir.
yes.
Can you explain a bit more slower?
Ma'am, your voice is a little bit low. Can you speak?
Can you explain it a bit slower?
Yes, you can also change it like a supercell, any structure you can go to the builder.
The speed of mic is too fast. The speed of explaining is too fast, sir.
Can you go a little slow, sir?
Little slow me.
Yeah, please make it a little slow because participants, some of them are not able to follow. You are going too fast.
Okay, sir. Okay, no issue. So like if you want to create a molecular based structure, so this is the molecular 2D builder. Here you can build any type of structure like boat structure, chair structure, and you can also study their equation. Like this is this type of structure if you want. So click on it and here you can apply data. Here you can see this is the structure that I have selected. And here you can define the force field calculation like UFF, GAFF. So I would like to select GAFF. And through this, if you want to create a 3D molecular structure, so click on the molecule. And here you can import your material. Like this molecule I have created earlier. So this is the molecule. And if you want to add some hydrogen atom, so this is the hydrogen. And if you want to add more atoms, so click on the plus icon. And here you can see this is the periodic table. And from this, you can select any atom. So this is the carbon and this is the different fragmentation. And suppose if you want to include carbon with a different, like this type of structure. If you want to include some oxygen, so this is the oxygen and different fragmentation I also selected. And if you want to include only oxygen atom, so click on only atom. And here I have selected oxygen. So you can see in a very quick time, you can simulate your molecular structure and click on the apply data. And if you want to design a molecular 2D structure, so like this is the cyclopentadiene and click on it. And here you can also rotate your, like this is the structure. Just 1 second. So I would like to select it and here click on the rotation part. And you can rotate like that. And if you want to select a single bond, like this is the single one, and here you can define like this is the carbon. If you want to add more, just 1 second. So select a single one and click on the carbon. Click a single one and here you can like that. Like this is the porphyrin based molecular structure. Click on again single bond. And again select the and again if you want to include this. And if you want to change this oxygen carbon with another atom, so click on the C option. And here you can see this is the periodic table. Click on the nitrogen. Any atom you can choose and you can remove like that. This is the nitrogen. This is also nitrogen. Nitrogen. And if you want to change this single bond with another double bond, so click on the double option. And where you want to like this is the double bond. This is also double. And click on the apply data. So here you can see this type of structure you can also study. And suppose if you want to import some material from this database, so I would like to click on the file option, go to the import and import local option. And here I would like to select this MOS2. This MOS2 material. And if you want to release some undesired atom from this structure, so simply you can draw a rectangle and select the atoms and click on the delete option. You can also delete like that. Here you can see in the direction of C, the vacuum is more. And if you want to reduce some vacuum from the direction C, so click on the convert to crystal option. And here you can decrease the vacuum. You can see the vacuum has been decreased and click on the build option. And if you want to make it centrally fit, so click on the center option. So the atom will be in the center position. This is the 3D viewer. From you can view like XY view, XZ view, YZ view, YX view, and ZX view. Like this is the XY view. And this is the XZ view of this CMOS2 structure. And if you want to simulate this structure, so then I would like to click on the simulator. And in the simulator, you can see this is the NanoDCAL that we have scheduled the presentation and demonstration. And this is the RESCU for DFT and DFT solver. And we also support the third parties to like this is the WASP, LAMS, Ovito, Quantum Expresso, Gaussian, Newton. So this third party tool is also there. So I would like to click on this NanoDCAL and go to the SCF calculation. Here you can define the electron temperature, cutoff energy, exchange correlation, LDA, GGA, meta GGA, and you can also define the K-point sampling, iteration control, density matrix, Hamilton matrix, total energy. And this is the basic settings, like this is the arrangement by element or by atoms. And you can also study like Howard atoms, some PDF combination. And you can also define your user defined, like this is the user defined neutral atomic database. This is the user defined, and click on the general. Here you can see this is the different combination. This is for the particular atom. And this is the virtual crystal approximation. So user defined neutral atomic database also you can study. And if you want to include spin like collinear spin, general spin, So you can also study like this is the collinear spin. And if you want to include general spin like a spin orbit coupling, so you can also study. So I would like to select no spin and click on this generate file. Once you click on this generate file, their input file will be generated. This is the project window where input and output file will be shown, and this is the property window where the information of your property of your structure will be shown. Like this is the MOS2, and here you can see total number of atom is 3, total area of this lattice, and this is the vector A, vector B, vector C value. Or if you want to show the particular atom, like this is the molybdenum and their coordinate point. And this is the job manager where the status of your project will be shown once you click on the run option. Here you can see after clicking the generate file, the SCF input has been generated. Right click and click on the open with. Here you can see what parameter we have selected, like this is the basic settings. Cutoff energy, exchange correlation function, K point sampling. Here no spin is included, and this is the station control, and this is the atom and their coordinate point. This is the Cartesian coordinate point. So click on the run option. And here you can define the number of parallel cores. Suppose if you want to run on like 5 core, 15 core, 20 core. So up to 128 core you can define. In my computer, 4 core computer is there. So I select only 4. And if you want to run the Java cluster, suppose so from here you can also give your remote location access and you can click on the run option to run the job. In the bottom of the page, you can see your SCF input is in the running condition. And in the meantime, if you want to analyze this property from this MOS2 structure, so click on the simulator, go to the NanoDCAL and click on the analysis part. Here you can define, like you can choose any parameter like density of state, effective potential, total energy, band structure, charge, Hessian, phonon band structure, electron density. So any parameter you can select, like this is the density of state, and here you can define the K point sampling for this density of state. And here you can define the number of energy point, energy range. If you want to show the band structure, this is the band structure, and this is the Brillouin zone path. Suppose if you want to remove any, like so click on here and click on preview and apply, so that you can select. And this is the potential, like effective potential, Harty potential, exchange correlation, neutral atom. This is the trans channel, Eisen state. Here you can define K space point, number of band. This is the effective mass, complex band structure. So any parameter you can study. Click on the generate file. Here you can see the analysis part has been generated. So you can run all the analysis part as well. So click on density of state, click on the run option. In the density of state, click on the open with. Here you can see what parameter I have defined. You can run the band structure as well. Click on the potential and run trans channel. So you can run on the analysis part in the Q condition. Once your SCF input calculation has been finished, then density of state will automatically start the calculation. And in the log file, you can see, click on the open with, and here you can see the parameter they are calculating. This is the background calculation that is running now, right now. This is the time taken, and this is the total energy, band energy, grid energy. So it will take little bit time to run this job. In the meanwhile, if you here you can see the SCF input has been finished. And density of state will automatically start the calculation. Here you can see this is in the running condition. Here you can see this density of state has been finished and their output has been generated. So click on the density of state and click on the show view. So this is the density of state with respect to energy of this CMOS2 structure. Here you can see this is the number of state and this is the energy minus 10 to 10. And if you want to zoom particular point like 5 to minus 5, so you can select like that. And also you can easily export your raw data. Suppose if you want to export this data, so click on the export option. And here you can see in which format you want to export, like JPG, PNG, BMP, PDF, text format. So you can also select like any format. This is the text format. And here I choose the desktop and click on the save. In my desktop, you can see this is the density of state that I have exported in text format. So you can easily export your raw data at any format. Here you can see the band structure calculation is also finished and their output has been generated. So click on the band structure, click on the show view. So this is the band structure of this CMOS2 structure. This is the conduction band, valence band, and this is the Fermi energy. And from here you can like select like middle of the band gap where you want to locate your Fermi energy. This is the middle of band gap, top of the valence band, bottom of the conduction band. So you can easily locate. Potential is also finished and task channel is also finished. Eigenstate is finished and their output has been generated. This is the effective potential. Click on show view. Here you can see this is the effective potential of this CMOS2 structure. This is the 3D viewer like XY view. This is the XZ view, YZ. So any view you can select and you can show. And this is the 3D viewer. And if you want to show the 2D, so click on 2D option. And this is the along X-axis, Y-axis, Z-axis. And this is the stereoscopic display along Z-axis, Y-axis, X-axis. And this is the 1D view. Along XY plane, YZ plane, XZ plane. So 3D, 2D, 1D view is also possible from this software. And you can click on the trans channel, click on show view. This is the trans channel. Suppose you want to zoom from here, you can also select any point. Click on the apply. And you can also change the Y minimum, X minimum. This is the eigenstate. Click on the show view. And here you can see this is the eigenstate. And if you want to increase like decrease, increase, so density will automatically increases and decreases. This is the 3D viewer, and if you want to show the 2D, this is the 2D view of this eigenstate along x-axis, y-axis, z-axis. This is the stereoscopic display.
Excuse me, I have a doubt. That is after we run this program, in the left side, suppose you have taken effective potential, and then we run the program for it. Okay,
Yes.
and then we want to see the output. Okay, so when we right click it, it will show open with containing folder. After we open with containing folder, the program is not getting open.
Like you want to show the background calculation, what the parameter they are calculating.
How do we open the? We have to open the containing folder, right?
Here you can see this is the eigenstate. All this parameter is there.
Yeah, yes. After this, how do we? The computer is unable
And
to
this,
open such
yes,
a
yes,
file. So
this software is also integrated with MATLAB. If you want to show their property and any value, so you can also, like I would like to open my MATLAB.
so we need to install MATLAB in order to open this.
Just 1 second. Here in the log file, you can see open with.
This is not
Like
opening like that for me.
Like this is the band structure calculation, and this is the parameter.
Okay.
Here you can see the calculation parameter, and this is the time taken.
But I wanted the plot.
So this is the plot, no? This is just. This is the plot of this eigenstate. Like click on this overview, and this is the 2D plot, and this is the 1D, like along XY plane, YZ plane, XZ plane.
Like, we take it and when we right click it and we have to open with something.
Yes, yes, yes. Open with, just I would like to show you. Click on the eigenstate, right click, show view,
Okay.
and here you can see. This is the 3D
Show
viewer,
view is not
2D viewer.
Show view.
And this, yes, yes. So right click, show view, and the structure will be shown. And this is the complex band structure, like real and imaginary axis. So you can zoom like that.
Excuse me, sir.
Yes.
Can this system predict the bonding and debonding states?
So just need to complete my this session, and after this session I will in the question answer session, so that time you can ask me and I will reply that.
Okay.
And also we have another session after this webinar, 3:45. After that we have one session another, and this time I will show you the device simulation. This is for the material simulation, and that session we will cover the device simulation. And if you want to create a supercell of this MOS2 structure, so click on the redefine crystal, and here you can see what like ABC value you can define. Like you can see, and click on the build option. And suppose if you want to make another supercell, so click on the redefine crystal, and here you can define 3 times in the direction of it, and click on the preview option. And suppose if you want to make a MOS2 based nanotube structure, so click on the build option And in the builder, you can see this is the nanotube. Here you can define the crawl vector, n and m value. And click on the preview option. So this is the nanotube structure, 8 by 8 nanotube structure of this CMOS2 structure. And click on the build option. And if you want to make a graphene based structure, so click on the build option. Like if you want to make a twisted bilayer graphene, so first you need to import the graphene. Click on the local. And in the 2D material, this is the graphene. This is the graphene. Here I would like to redefine my crystal in the direction of A and B. So 30 time in the direction of A and 30 time in the direction of B. And click on the preview option. Here you can see this is the graphene sheet, and click on the build option. And suppose if you want to increase the vacuum, so click on the convert to crystal option, and here you can define the vacuum like 30. Here you can see in the direction of C, the vacuum has been increased. And click on the build option. And to make another layer of this graphene, so click on the graphene, and here you can again redefine the crystal in the same way like 30 times. And click on the preview option. And click on the build. So you can copy all these graphene atoms, Control C and Control V inside this tube. And suppose if you want to rotate this graphene, so select all this graphene and click on the rotation. This is the move option. Click on the rotation. Here you can also define the angle and like in which direction you want to rotate, like this is the screen vector XYZ axis. So in the direction of Z, I have rotated. From this structure, you can see the graphene has been rotated. And if you want to make it center, so click on the center option. And suppose if you want to make a nano ribbon based structure, so click on the build option, go to the nano ribbons. And here you can see, if you want to make a boron nitride based graphene nano ribbon, so select the boron, this is the boron. And this one is from the nitrogen. And here you can also define the bond length. And if you want to passivate with hydrogen atom, so click. And if you want to define the structure like a crawl vector n and m value, and click on the preview option. So this is the boron nitride base structure, and click on the build option. Again, go to the redefine crystal, and you can redefine as per your need, like 10 times in the direction of C. C direction is also called transport direction. Click on the preview option and click on the build. If you want to add a multi-layer structure, like this is the single layer. If you want to add one more layer, so select all this atom and click on the mirror option. Here you can define the XYZ normal vector, like this is the XY, and here you can define the distance. Copy this checkbox, click on apply. This is in the XY direction. If you want to include in the XZ direction, so select all these atoms and click on the XZ, and here you can define and click on the apply. If you want to move these atoms, so select these atoms and click on the move option. Here you can select like in which format, like a XYZ, unit cell vector, a screen vector. So this is the screen view. If you want to change it with another atom, like this is the boron nitride and this one from the carbon. So click on the replace atoms, and here you can select the carbon and click on the OK. So this is the boron and boron nitride and graphene based structure, multi-layer structure. This is the distance. Just one second. This is the distance measurement. If you want to measure the distance between these two atoms, any two atoms, so select two atoms. Here you can see this is the distance 3.475. And if you want to measure the angle, so click on the angle measurement and select the atoms. You can see this is the angle between these three atoms. And this is the dihedral angle measurement. So the angle between four atoms. And this is the vector measurement. If you want to measure the vector, like click on the vector option and select the atoms. And if you want to make an interface, like this is the builder, you can see this is the interface builder. Suppose if you want to make an interface between boron nitride and carbon based atom, so first you need to select the graphene, carbon and boron nitride, like this is the import local. This is the carbon primitive cells. And this is the boron nitride primitive cells. So again, I will go to the build option, click on the redefine crystal, and here I would like to define. and click on the preview option. Again, go to the carbon, go to the builder and go to the redefined crystal. And here you can redefine. And click on the preview option. And to make an interface between these two, so click on the builder and go to the interface builder. Here you can select like this is the carbon redefined crystal, and this one is the boron nitride. Click on the mesh option. Here you can see the total number of atom, angle, rotation, mismatching, area, strain, and this is the strain's first surface, second surface, and both surface. Click on the preview option. Here you can see this is the interface between this carbon and boron nitride, and click on the build option. And if you want to change this carbon from another, so click on select all this carbon and go to the periodic table. This is the phosphorus and boron nitride. And if you want to create a defect in your this structure, so select where you want to create the defect. Suppose if you here want to make a defect, and based on the defect,
Excuse me, band structure of this interface.
yes. Can you repeat your question once again?
Sir, please continue.
Okay.
Sir, can you unmute?
Yes.
Sir,
Can we find the band structure of this interface?
Deepak sir, you are
Sir, you are not audible. Hello, sir. You are not audible.
So
Can
yes,
you-
yes.
Yes, now it is fine.
Okay. So go to the simulator if you want to show the band structure of this structure. So click on the NanoDCAL, go to the SCF calculation, and first you need to generate this file, input file. This is the SCF input, and again you can go to the simulator NanoDCAL and in the analysis part. Here you can select the band structure, and here you can define the line zone path as per your need, and click on the preview and click on the apply. And here you can also define the number of K point and click on the generate. Here you can see the total number of atom is more, so this will take time to calculate the property.
Okay, thank you.
If anyone has any more issue like question, any other question, so you can unmute your mic or you can chat in the box so that I will try to resolve it. And in the second session, I will cover the device part, device simulation. This is the builder. If you want to create a surface slab, surface clean, so here you can define the Miller indices, scale value 1, 0, 0, any combination you can define. And here you can also add the vacuum. You can also create the slab. You can also study increase the thickness. Vacuum you can also create. Like I would like to select the gold atoms, purity material, conductor, pure metals, and this is the gold. Go to the builder, redefine crystal, and this is the face centered cubic structure, and this is the body centered cubic structure. So I would like to click on the face centered, click on the preview option, and here I would like to click on build. To make a surface with structure, so click on the surface slab, and here you can define the scale value, Miller indices. You can also include the slab. And if you want to add some vacuum like this, and click on the build option. If you want to make it center, so select all these atoms, click on the center option. You can also stretch your cell like this is this for the stretching the cell, food cell. This is the wrapping the cell. This is the stretching the cell. Here you can define where you want to stretch, like in the direction of A, B, C, alpha, beta, gamma, any value you can change and click on the apply. And click on apply. You can see. Like this is my MATLAB is opened, and I need to select this project. Like this is the project. This is the MOS2 and their output file. This is the bind structure .mat file. Double click. Here you can see my project has been loaded, and click on. Here you can see this is the parameter that I have defined, and this is the value.
Sir, you can take a break at 3:45. We have some question in our chat box. we can again start at 4 o'clock.
4 o'clock. Okay, no, so
So, sir, there is a number of questions. First one from Manodeepan Sahu. WSE2 can be analyzed using this software.
yes, WS. Can I show you?
You can, sir.
Yes, okay, one second. Like this is the file option, import local. And this is the 3D layer material. And here you can see this is the WSE2 and WSE2. So which one included in the chat box? Like WSE2 or just 2?
WSE2.
WSE2. So this is the WSE2. Just one second. So this is the WSE2. So like which property you want to calculate from this like a WSE2? Which parameter you want to calculate?
That is not mentioned in that question, sir. So second question is that can we add, that is from Saurabh Chauhan. He asked, can we add new materials dataset?
Yes, you can add like just one second. Suppose you are working on any other third-party software, like this is the import option. And here you can see, and this software support like this type of file like a data SZ, XYZ, CIF file, postcard file, XSD file. So this type of file format you can easily import. Or if you want to have, if you have any other format, so click on the convert file, and from here you can select your file and you can easily convert. Like in which format, like this is the SZW and this is the XYZ. And if you want to like if the material is not in the database, so you can also import from the online database. So this will make a third party interface with the API, and here you can select and click on the search option, so the item will be shown.
Another one question from Dr. Siva Janbi. She asked, sir, is there any free software to measure the density of state and band structure of the nanoparticles?
Fees means?
Free.
Free software.
Free software.
So I have no idea about the open source software, and this software is a commercial software. So if you want to measure this property like density of state, band structure, any nanoparticle, so you need to purchase.
Another one question from Kumar Somo. He asked, how can we get the refractive index and extinction coefficient from the material from this software?
Refractive index is also possible. You can analysis. Just one second. My system is running little bit low.
Sir, can we reply the next question?
Yes, you can ask.
That is from G. Kusuma Priya. She asked, how can we measure quantum observables?
Quantum observation.
Observables.
I need to check this point in my.
Okay, sir. Next one is from Silpa M. How can we calculate nonlinear susceptibility?
So this software is NanoDCAL is for the molecule, crystal, and device simulation. And if you want to work only on the material specific, like if you want to calculate any susceptibility property, so select this DFT. And here you can select what parameter like phonon density of state, phonon structure, phonon optical property, Raman spectra. So any parameter you can select, and based on there, once you run this file, so in the output file, like once the calculation will finish and their susceptibility output will be generated. So this is the device studio, and that is a user interface for this NanoDCAL and RESCU software. So to create a device structure, first you need to import the electrode for like a left electrode, right electrode material. So I would like to click on the file option and import the material from my local database. This is the 3D material, conductor, pure metals, and this is the gold atom. So I have imported this gold atom from my local database. So I would like to again go to the builder and again redefine my crystal. So this is the face center cubic structure and this is the body center. So you can preview, this is the face center and this is the body center cubic structure. So I would like to click on face center cubic structure, preview, and click on the build option. To make a supercell like structure of this gold atom, click on the build option, again go to the redefine crystal. And here I would like to redefine in the direction of a 2 times in the direction of V and 4 times in the direction of C. Click on the preview option and go to the build option. So this is the supercell of this gold atom. If you want to show the XY view, so this is the XY view of this gold atom. If you want to remove some atom, so you can draw a rectangle and select and click on the delete option again. So you can delete the atom as per your need. Again, I go to the ZX view and I want to delete some more atoms and deselect these atoms. So this is the gold atom that I have built as per my requirement. If you want to create a vacuum in the direction of, yes. If you want to create some vacuum in the direction of a direction B, so again click on the convert to crystal option and here you can define the vacuum like 20 times in the direction of A, 20 times in the direction of B. Here you can see the vacuum has been created. Click on the build option. To make it centrally, so click on the center option and here you can choose the along x-axis, along A, and this is the along B. If you want to make a two terminal like this is for the left side and if you want to again create a right electrode, so you can just select all these atoms and go to the mirror atoms and here you can define like this is the XY and here you can define the distance between this electrode. Copy this checkbox and click on the apply. Here you can see the mirror has been created and if you want to show this like this electrode and this electrode in between the unit cell, so again click on the convert to crystal option and here you can increase the vacuum in the direction of a C so that both the electrode in between the unit cell. You can see both electrode in between the unit cell and click on the build option. If you want to make a molecular based device structure, to prove device structure, if you want to include some molecule in the center position, so you need to import this atom. Either you can import or you can create your own molecular structure. So I would like to import local 0D material. This is the molecule. And if you want to include some benzene, like this is a benzene, you can select all this benzene. This is the benzene. You can select this molecular structure, Control C and Control V inside this unit cell. Here you can see this is the benzene molecular structure. Select this one and click on the center option. If you want to rotate this structure, this molecular structure, so select this structure and click on the rotation option. Here you can define the angle as well, angle 90 degree. And again, if you want to rotate 45 in the direction of Z, so you can see I have rotated this benzene structure. And if you want to add an atom between these two atoms, so select these two atoms and click on add a new atom. Here you can select this is the new atoms, and if you want to change it with another, so select and click on the replace atoms. And here you can select, like if you want to make it sulfur base, so you can see this is the sulfur. And if you want to add here, and you can change like that. You can move this electrode like click on the move option. Here you can select like along the screen view, and you can move this atom as well. So that all the atom will connected between by the covalent bond. So and you can click on the recalculate linker bond, and here you can see sulfur. This is the sulfur, this is the hydrogen, and this is the gold atom. All this is connected with by the covalent bond. And if you want to reduce some vacuum, here you can see vacuum is more. And here you can click on the center. And if you want to make a device structure, so you can click on the convert to device option, and here you can define the electrode like left electrode, right electrode, bottom electrode, top electrode, front electrode, and back electrode. So you can define up to 6 probe device structure. You can simulate like here I selected left one and this is the right one. You can also change the point of this like electrode. And click on the preview option. Here you can see this is the left electrode and this is the right electrode and this is the center region. Click on build option. So this is the benzene based molecular structure, and here you can see this left one is AU electrode and gold electrode, and this right one is also gold based electrode. If you want to change with another like this gold, click on the replace atoms, and here you can define like this is the silver, left one is silver, and the right one is gold atoms. Just one second. This one is the Argentina one. Okay, you can see this is the silver, left one is silver and right one is gold electrode. And if you want to analysis the structure from this, like the device structure, so click on the simulator and select this NanoDCAL, and first you need to generate the SCF file, like self-consistent field calculation. And here you can define the electron temperature, cutoff energy, exchange correlation, LDA, GGA, meta GGA, K-point sampling, contour integral. You can also define the electrode temperature, electrode voltage, K-point for electrode left one, and you can also define electron temperature, electrode voltage, and K-point for the right one. This is the iteration control, density matrix, Hamilton matrix, and this is the basic setting. This is the Howard atom. And if you want to include some doping, so click on the doping, and here you can select what type of doping you want. Like this is for the user defined doping, and you can select. If you want to change it with another, like this is the atoms. And if you want to include some spin tonics application, collinear general spin, so you can also include, and click on the generate file. Here you can see the input file for the left one, right electrode, and for the center position is generated. This is the left one. This is the parameter for the left electrode, and this parameter is for the right electrode. And this is the center region. And if you want to analysis some property from this structure, so click on the simulator, go to the NanoDCAL, click on the analysis part. Here you can choose what parameter if you want, like density of state, effective potential, total energy, scattering state, transmission, photocurrent, IV curve, charge, electron density, potential, conductance, thermoelectric current, Seebeck coefficient. So this type of structure you can simulate. Like this is the photocurrent. Here you can define the polarization basics C1 and U2, and this is the polarization vector, like linear polarization, oblique polarization, elliptical polarization, left circular polarization, right circular, elliptical, oblique is there. You can also define, and this is the value of theta. You can also define the minimum angle, maximum angle, and this is the interval. And if you want to include the photon energy range, so this is the minimum, maximum, and this is the interval. This is the K point sampling for this photocurrent. And if you want to irradiate your atoms, like if you want to fall the light on the center region, so you can select the center one and you can click on the select option. You can click on the OK. And this is for the IV curve. Density of state, effective potential, total energy, scattering state. So you can also study. Click on the generate file. You can right click on the SCF input, click on the run option, and you can run the job and click on the run option. Since this calculation will take time to calculate the property and we have a very limited of time, so I have just cancel this job and show you more property. And if you want to create a 3-terminal device structure, so go to the simulator, NanoDCAL, and here you can see this is the transistor. Here you can also define the thickness and dielectric permittivity, and this is the thickness. Here you can see this is the gate region. And here you can define the gate voltage. Here default value is automatically selected. You can also define as per your need, like 0.5, 0.7, any value you can select. And here where you want to show your gate, like gate region, like a top and bottom, front and back. And this is the region of gate. Suppose you can see the region of the gate is reduced. And here where you want to like source left side, right side, and also you can define the bias voltage. Here you can also change the temperature of this electron for the left one, right one. This is the contour integral for this IV calculate 3-terminal device structure. This is for the electrode, left electrode, right electrode. Same as the 2-terminal devices. Here you can see. And click on the generate file. This is for the 2-terminal devices, 2-probe device structure. This is for the 2-probe device structure, and this is for the 3-terminal. Here you can see VD voltage is 0.2 and the gate voltage is 0.5. Bias voltage is fixed, drain voltage, and gate voltage is changes. And their input file, SCF input file, and their IV calculation is generated. So this is for the 3-terminal device structure. And if you want to make a 4-probe device structure, so just 1 second. I make a copy this job. And click on OK. And you can select all these atoms. Control A. Just 1 second. And you can rotate. Just one second. First, I need to remove this molecular structure. And increase some vacuum. Click on the build option. Select all these atoms and click on the rotation. Control V inside this. We'll see. And Control V. You can select this one and you can rotate. You can move this structure. Here you can define the distance like this one. And just increase the level of the vacuum like just here you can increase in the direction of a 30 and P is also 30. Click on the build option and go to the center position. So you can build your structure as per your need, like I am moving these atoms and this one also. And suppose if you want to make a molecular structure in the center position, like porphyrin based phenylacetylene. So I need to select this molecular structure. Click on the import local. This structure I have calculated earlier, designed earlier. This is the through this builder, molecular builder, you can design this molecular builder. You can design the molecule, and you can select. You can select all these atoms. Control C, and paste this unit cell. You can select this one molecular structure. Go to the center position. Just increase some more vacuum. And click on the build option. Okay, that's fine. And you can select this one, this molecular structure, and click on the center position. Here you can see. And if you want to rotate like this molecular structure, select this one and go to the rotation option. And here you can define like this is the angle 90 degree. Yes. We need to add some more vacuum in this in direction of C, like 45. Build option. Select this electrode, move option. And go to the rotation option. Okay, that's fine. And if you want to include this covalent bond between these two, so click on the recalculate linker one and just move this one. And again click on the recalculate linker one. And go to the convert to device option. And here you can define the electrode like left one, right one. This is the far bottom and top. So this is the 4 probe device structure. Click on the preview option. So here you can see. And click on the build option. This is the top electrode. This is the right one, left one. This is the right one, and this is the bottom one. If you want to change with another atom, left, right, and bottom and top with the different atoms, so you can select. And you can go into the replace atoms, and here you can select any atoms. So this is the aluminum. This one is gold. This is the boron. And this one silicon. So for electrode, this is the silver, boron, and this is the silicon, and this is the gold one. This 4 probe device structure is very useful for the resistivity measurement, and This is the reason why using the 4 probe device structure over 2 probe because of the force and sense probe. So it is eliminate contact resistance and increase the accuracy. And again, you can go into the simulator, NanoDCAL, and go to the SCF calculation. And here you can set up the parameter as per your requirement. If you want to include spin, this is the collinear spin. And this is the general spin, and this is the spin orbit interaction, and click on the generate file. This is the right electrode input for the right devices, and this is for the left one, and this is the right, bottom, and top. So the SCF input for all the electrode has been generated, and for the device is also generated. And again, you can go into the simulator, NanoDCAL, and you can do the analysis. You can choose any analysis part, like this is the density of state, effective potential, total energy, scattering, transmission, photocurrent. This one is the IV, and click on the generate file. And suppose this is the benzene structure, and if you want to do some optimization, so click on the simulator, go into the NanoDCAL, and go to the relaxation. Here you can set up the parameter, this 2 method like molecular dynamic and conjugate gradient. This is the molecular dynamic, and here you can choose the force convergence criteria, and you can click on the generate file. So relaxation is also possible from this software, and you can click on the run option. You can click on the run. I have this calculation will take time, so I have calculated this project earlier. So I would like to open my device, new project, and just cancel this job. And I can show you some analysis part. Here you can see, and this is the 2 probe device structure. And this is the analysis part. This is the density of state of this structure. And this is the transmission. So view. This is the transmission coefficient with respect to energy. This is the current voltage. This is the total electron density. If you want to increase the density, this is the decrease. Here you can see the level of the density is increased. And you can click, and this is the 3D viewer, and this is the 2D view along x-axis, y-axis, and z-axis. This is the stereoscopic display along x-axis, y-axis, z-axis. So you can rotate like that. And this is the 1D view of this total electron density along xy plane, yz plane, xz plane. And this is the effective potential. Along x-axis, y-axis, z-axis, and this is the stereoscopic display. This is the plane display. You can also change the color maps in GP spectrum. So any value you can change. And this is the 1D view. So 3D, 2D, and 1D view is also possible. This is the Seebeck coefficient along temperature and along chemical potential energy. You can also define spin up, spin down calculation. And this is the temperature. If you want to show at a particular temperature, like blue one is spin up and red one is spin down calculation. And for the IV calculation, thermoelectric current, you need to integrate it with the MATLAB. This is the MATLAB. Here you can see this is the conductance and current MATLAB file, and this is the current voltage curve MATLAB file. And here you can see the data like output and input of the voltage. Here you can see I have applied, and the V1 is 0.1 and V2 is minus 0.1. And accordingly, the in current value will be calculated. Like this is the I1 and this is the I2. You can also show the conductance. There is no current and voltage is applied. And this is the thermoelectric current. There is no voltage is applied, 0, 0. So either from here you can apply the voltage like a simulator, NanoDCAL. Either here you can define the voltage, from here like SCF, go to the SCF input, right click, open with. Either here you can define like 0.1 and minus 0.1. So any value you can define, and you can calculate the IV input output. So this is for the 0.1. This is for the 0.1. 0.1, and if you show the 0. For the 0.3, this is for the 0.3. Here you can see V1 is 0.3 and V2 is minus 0.3, and the I1 and I2 is calculated. And if you want to show the plot, so you need to write the script like this is, and here you can write. Once you can do the simulation for the different voltage, then you can draw the IV curve. Like here, I have calculated like this is the here you can see the current is 6.22. This is for the 0.3 and 0.1 is for the minus plus 4.3099. You can also define the level of x, where we want to show voltage on the x or y axis. On the x-axis is voltage and y-axis is current. And you can run the job. You can see. Once you run this job, the IV calculation curve is plotted. Here you can see. Once you calculate the simulate the property like a IV and will define the voltage properly, then this graph will be accurate. Here you can see for 0.1 is minus 4.309 and 0.3 is 6.22 that I have put up. Like here you can see minus 4.309, 6.22, and also I have calculated for the 0.7, 0.9 as well. This is for the 0.7. And here you can see the output 0.7 and minus 0.7, and this is the value. and for 0.5 as well. This is for the 0.5. There is 0.0. So you can simulate and you can also plot this IV calculation through MATLAB. And if you want to make a bilayer CuPC molecular based device structure, so first you can go into the builder, go to the nano ribbons, and here you can define the crawl vector like a 4. I have selected 4x4 and click on the preview option. So this is the 4x4 graphene nano ribbons and click on the build option. And you can redefine your crystal as per your need, like 20, and click on the preview. And you can delete atom as per your need, like if you want to include from the center position, like this is the XY ZX view. If you want to delete this one, select and click on the delete option. If you want to delete, so you can delete like that. So as per your need, you can delete. And if you want to include CuPC molecular structure in the center position, so you need to select this CuPC. I have created this molecular structure earlier, so I need to import local, and this is the 0D molecules, and this is the CuPC. Just you need to copy this molecular structure, Control C and Control V inside this unit cell. You can select this CuPC molecular structure and click on the center position. You can select and you can rotate like in the 90-degree. Just 1 second. First, we need to move this molecular structure in the left direction. Go to the rotation. So you can adjust as per your requirement, like just you need to move these atoms so that both and click on the recalculate linker one. Okay. You need to move these atoms, these graphene atoms as well. And then go to the recalculate linker bond. So this type of structure you can also simulate. You can adjust the vacuum as per you, like this is. You can also remove from the direction A and direction B. And then go to the convert to device option. Here you can define the left one and this is the right one. And click on the preview option and you can also change if you want. Like this is the file. And click on the preview option. And here you can see. This is the CuPC based molecular structure. Left electrode is graphene and right one is also graphene. And click on the build option. Just 1 second. And again, you can go into the simulator and you can do the analysis. Like this is the NanoDCAL SCF calculation. And here you can define the parameter, whatever parameter you want. And you can click on this generate option. So their input file for the left, right, and device part is generated. And you can do the analysis as per your need. So I have created this project earlier, so I need to import. This is the this is the bilayer CUPC. This is the structure. And this is the analysis part. Like this is the transmission of this structure. Click on show view, and this is the transmission. And this is the total electron density. And this is the 3D viewer. This is the 2D view of this structure. Along x-axis, y-axis, z-axis. And this is the stereoscopy display. This is the 1D view of this along XY plane, YZ plane, and this is the ZZ plane. Again, I am opening my existing project that I am working. Like this is the project. And in the builder, you can see this is for the nanotube structure. You can also simulate like disorder graphene like structure. Like this is the disorder graphene structure. And here you can define the bond length, the supercillion, and N1 and N2. And you can also preview. Yes. If you want to change like click on the preview. Here you can see. And if you want to change with another atom, so from here you can select. This is the boron. This one is also boron. This is the nitrogen. So after selecting this boron nitride, you can click on the preview option. And you can click on the build option. And if you want to make a multi-layer structure, so just you can copy this, select all these atoms, go to the mirror atoms, and here you can define the position like normal vector x, y, y, z, x, z, y, z. And here you can define the distance between these two layer structure, and you can click on the apply. Here you can define the position like a XZ. So this is the multi-layer structure. And if you want to include some defect in this structure, like where you want to create a defect, like if you select this one, you can see the defect in the sheet has been created. And based on their simulation, you can also study the band structure, how will be the band gap. And this is the discharging plane like structure. You can click on the build. Here you can also show this is the icosahedron, cubectohedron. This one is the icosahedron. And here you can define the cell, number of cell. And here you can define the bond length, and you can also select the element, like this is the carbon. And this is the icosahedron of this carbon atom. If you want to change with another, like this is the oxygen. And you can build. So this is the icosahedron. And if you want to show cubectohedron, so click on the cubectohedron, and here you can choose the number of cell, define the bond length, and click on the preview option. And like this is the device structure. If you want to add some buffer, like go to the simulator, go to the NanoDCAL, and from here you can add some buffer, like left side, right side. You can see the buffer has been created in the left side. And if you want to also include in the right side, so just increase. So you can also include the buffer. And like I am going to select some WSET based material, like this is the 3D material, layer material, and this is WSE2. Delete these atoms. And if you want to make a supercell, so click on the builder and go to the redefine crystal. Here I am increasing in the direction of C 10 times and click just once. The direction of A and direction of B. And click on the build option. From here you can also change their coordinate point, like this is the alternate coordinate. And if you want to convert it into device, so click on the electrode option, like bottom one and top one, and click on the preview option, click on the build. If you want to change this, tungsten with the molybdenum, so click on this tungsten and go to the replace atoms, and you can select the molybdenum, like this is the molybdenum, and click on the OK. This is the WSE2 and this is the MOS2. WSE2, and this is the MOSE2, and you can also change in this one. From this molybdenum, and click on the OK.
Hello, sir. There is a question.
Yes.
Kashish asked, he is not able to import the online data. Can you show it once? How can we do that?
So I think you have the trial license. Yes.
Kashish,
Because in the
do
yes,
you have
because
the
in the
access?
because in the trial license there is some limitation. You cannot import the material from online database.
Okay, sir. Thank you for the clarification.
Okay.
Sir, can you show the device making for TMDs different layers, like 3, 4 different for making 4 probe?
Like this is the four probe device structure.
If we taken a different TMDs, can you show the once again, if you don't mind?
Okay, no, so I can show you. Because 4 probe will take some time to design the structure. So like this is the gold. You can go into the builder option, and here you can define a supercell like a 2. As per your need, you can define like a 2 to 4, and click on the preview option and go to the build option. You can, this is the XY view. Click on this and delete. Click on this and delete. Again, go to the ZX view. You can deselect these atoms and click on the delete option. Go to the convert to crystal option. Here you can define the vacuum, the direction of it 20 times, and B is also 20. Click on here, you can see the vacuum has been created, and you can click on the build option. If you want to make it in center, so click on the center position along center A and along center B. And if you want to mirror of this electrode, so select all these atoms and go to the mirror option. Here you can define like this is the XY, and here you can define the distance. Copy this checkbox, click on apply. You can see the mirror has been created. If you want to show this both electrode in between the unit cell, so click on the convert to crystal option and go to the ZAN, that is transport direction. Here you can define the value. And you can show the vacuum has been created and both electrode in between the unit cell. Click on the build option. And again, if you want to make a 4 probe device structure, so then you can select all these atoms, Control C and Control V. After deselecting, Control V. Here you can see the atom has been copied. You can select all these atoms and go to the rotation part. Here you can define the angle as well, and you can choose where you want to. So like this is the y-axis, minus y-axis, x-axis, and this is the minus axis, and this is the z-axis. In the direction of z, yes. And you can go into the recalculate linker bond, yes. And again you can select and move these atoms. And again, you can go into the convert to device option, crystal option. And here you can define the vacuum, like in the direction of the 2 times, and click on the build option. Go to the center position. You can move these atoms. You can select as well. And again, you can go into the convert to crystal option and define some vacuum in the direction of C. And click on the build option. And here you can move these atoms as well.
Hello.
After reaching that level, is there any particular choice of a material when we put inside this kind of
Yes. You can put any material. Any material, either this one is gold. If you want to change, so you can select all these atoms and go to the replace atoms. From the periodic table, any atoms you can choose.
Like as when you are adding the organic structures, so like if we want any inorganic materials, so can we put in there?
Like in the center position, molecular structure,
Yes.
different structure. Yes,
Yes.
you can. Yes, you can put.
One more
So,
thing, sir.
yes.
Can we calculate Fermi surfaces from this tool?
Fermi structure, and that is
Fermi
from
surface,
the
like Berry curvatures.
die curvature. I need to check this point because I have. Like if you want to add any molecule, another molecular structure in this center position, so go to the file. Either you can create from the molecular structure, molecular 2D. Either you can import from the local database.
Sir, while importing, can you show how to import zip file in Device Studio?
Yes, if you have the zip file, so you can go into the file option, import local, and you can choose your file, like where your file is located. Here you can see like XYZ CIF file, XSD postcard will automatically import it. Once you select file and click on the open, then your file will be selected.
Thank you, sir.
Sir, there is two common questions in chat box, one from Sapam and one from Scientica. Can we make heterostructure using this simulation?
Yes, to structure you can also study. Just 1 second, I can show you. Like this is the gold atoms. And first I need to import another atoms. And this is the conductor, pure metals. And this is the silver. Go to the builder option, go to the interface builder, and you can select this gold and silver. This one is gold and this one is silver. You can click on the match option. Click on the preview. Here you can see this is the total number of atoms, angle, rotation, mismatching. This is for the stain first surface, and if you want to show second, click on the match option. Here you can click on preview. So this is the second surface. And if you want to show both surface, click on the both. click on the match option and go to the preview option. So this is for the both surface. And you can click on the build option. So this is the heterostructure base. And also you can do the study like go to the simulator, define the some parameter SCF calculation. Here you can define whatever parameter you want. If you also want to include the spin, collinear general, and you can click on the generate file. This is the script that automatically generated once you click on the generate file. This is the basic setting. Collinear spin is defined, and this is the iteration control. And this is the atom, number of atom is 102, and this is the Cartesian coordinate point. And you can do the analysis. Whatever parameter you want, so you can click on and generate. Any more question?
We are finished.
Kartis is asking about can we find the refractive index versus wavelength curve for certain material?
1 second. Yes, just 1 second, I can show you. Go to the simulator, NanoRescue, and you can click on the DFT solver, density function perturbation theory. And here you can choose the optical property. This is for the LDAGG, and this is the damping factor, field direction, and you can click on the generate file. Just 1 second, I can show you for the this gold atoms. Run this CSCF input. You can click on the run option, and this for the dielectric. This is the phonon input, and this is the optical input. Once this calculation will finished and their wavelength graph will be generated. Just wait for some time. In the meantime, if you have any more questions, so you can ask.
Sir, one more question for Sayantika. Can you please show how to make mixed dimensional heterostructure device like MOS2 nanoribbon, WS2 quantum dot, SI, that kind of structure?
Any structure you can select, go to the build option, go to the interface builder, and here you can select any atoms like this is the WSE2. And again, you need to just 1 second. First, I need to import the material. This is the This is the MOS2. Where is WSC2? This is the WSC2. Okay. So you can select this MOS2. Go to the builder, and here you can redefine in the same ways as you can define in the WSC2. And then you can go into the build option, go to the interface builder, and here you can choose like this is the WSC2 and this is the MOS2. Click on the match option. Here you can preview. So any type of structure, heterostructure you can study.
One more question from Hanson D. Souza. Is it possible to add porosity in the material? Is it possible to add porosity in material?
I am not aware of that point, porosity. So
Sir,
yes,
you said we can get the graph for refractive index versus wavelength. So can we get
wavelength.
the
Yes, you can see here
points
the calculation is in the running. The calculation is running.
yeah. So along with the graph, we will get the data points also.
Yes, yes. Can you repeat? Data for the
Uh, Along with the graph, can we get the data points at like
Ye-
the refractive index at each
yes,
wavelength?
yes. Based on their data point, the wavelength graph will be shown.
Okay, so along like what are the optical properties that we can get from these simulations along with the refractive index? Can you like
Just
briefly elaborate?
just 1 second. After finishing this, I will show you.
Okay, okay, great.
Any more question?
Sir,
Yes.
let me check.
Here you can see, and this is the wave function of this gold atom. And this is the potential. This is the density. and optical is in the running condition. This is the out dielectric input. You can see this is the NanoDCAL for DFT and a NEGF solver, and this is the advanced version of this NanoDCAL, and this is the RESCU for DFT and DFT solver. And this is the advanced version of this RESCU that is written in Python and Fortran. And this is the spin qubit for the spin qubit devices, QTCAT. Our Schrodinger equation. And you can click on the NanoDCAL. And this is the theory, and their tutorial is also mentioned. Like this is the DFT in NanoDCAL. And this is the post analysis, like band structure and their equation. This is the complex band structure and their equation. Scattering density of state for the scattering region. Charge. You can also visit our website, and if you have more questions, so either you can send us an email or you can directly contact with the given number.